So we are being asked to use an annual growth rate of 1.4% in a 20-year period for a certain population to find the approximate doubling time and then predict the population in 2050 based on a 2000 population of 5 billion. There's a lot of numbers in here. Let's take it one thing at a time. The first thing they want is what is the approximate doubling time. Now, there is an exact doubling time formula, but they said approximate. If you don't already have that formula written down, please do so, or memorize it. It's actually a pretty small formula. Let me bring up our notes here. 8. Now this is an increasing, going to be around here, and the approximate doubling time formula is 70 divided by p, where p is the percentage not converted to a decimal. This is the one time probably in your whole math career that you will not be converting a percentage into its decimal form. So the first thing I'm going to do is find my approximate doubling time by doing 70 divided by the percentage I was given. The only one I was given was 1.4. So 70 divided by 1.4. Not doing that in my head, so let me open my calculator. 70 divided by 1.4. And I get 50. That's actually pretty nice. That's 50. So it looks like the approximate doubling time is 50. And we're talking about years here. Everything was years, so it's 50 years. So now they want us to use this information to approximate what the population would be in 2050 if the population in the year 2000 was 5 billion. Now, lots of times when I see the word billion or million written out, I like to write out the whole number. But I do notice that after the answer box right here, they have the word billion. So because those two match, I'm not going to freak out too much about changing 5 billion into an actual 5 with a bunch of zeros after it. So I'm just going to leave it as a 5. If this had not said the word billion, then yes, I would have written out 5 billion as a string of numbers. Okay, so let's go back to the notes for our formula. Now we know what the approximate doubling time is. Now we have a formula here to find a new value based on an initial value. Now our initial value is the 5 billion. We know that the big T in this exponent here is the doubling time. We just calculated that. It's 50 years. Little t is the time passed. That's the one thing they didn't explicitly say. But we can figure that out because they say that the population was 5 billion. Or 5.0 billion, however if you want to put the 0.0, that's fine. But it was 5 billion in the year 2000. We're predicting it in 2050. So how many years have passed between those two? Well, 2050 minus 2000 means 50 years have passed. So my little t is 50. My big T also happens to be 50 because big T, remember, is the doubling time. So if I'm going to go ahead and use this formula here, my initial value is the 5.0. Then I have to do times 2. That's going to come next. There it is. Times 2. And it has an exponential fraction of little t, which is this, divided by big T, which is this. Now, it's not very common that little t and big T, the time passed and the doubling time, are the same. In this particular case, they just kind of cancel, they just cancel out, and you end up with 5.0 times 2 to the power of 1, which is the same as 5.0 times 2, which is the same as just 10.0. But just for the sake of just doing this out, because these two numbers aren't often going to be the same. They might be, but not always. Let's go ahead and put this into Desmos just so you can see it out anyway. And we can verify that I did do my little mental math right. So let's plug this into Desmos. So there's our previous calculation. So starting at 5 billion, and it is doubling every 50 years. And we want to know how much it will be at after 50 years. And there we go. We get 10. So I guess I shouldn't have circled that. Usually circle final answers. So what is the approximate doubling time? 50 years. Will the approximate population be in 2050? 10 billion.